A quick reminder, labs and mini projects can be done alone or in a group of two, but for technical reasons on Moodle, you must be in a group, even if you're alone. That seems paradoxical, but we need that. So please don't forget to join a group on Moodle, even if you're alone in your group. You will not be able to upload the lab if you're not in a group. Voilà. Let's recap a few things we saw last week. Last week, we computed confidence intervals that summarize with one number a distribution, the central value of a distribution. And we've seen that there are two metrics that are used classically for that, the median, and computing a confidence interval for the median is done with this method. For example, if we have 100 data samples, we need to use the order statistics from the data sample, assuming it's IID. And then for 100, we take the values at rank 40 and 61, and that gives us a confidence interval at level 95%, which summarizes the uncertainty about the median estimate itself. Very often, it's not the median that is used for good or bad reasons, but the mean, and computing a confidence interval for the mean can be given by this formula. If we are at level 95%, we use the magic number 196. We take the sample mean plus or minus 196 over square root n, an estimate of the standard deviation. And this requires two assumptions. One, that the distribution has a finite variance, which of course is required in order to have meaningful interpretation of the estimate of the standard deviation. And n must be large. So this is an approximate formula, which is not true for any distribution, but is true if the number of samples is large, and that comes from a central limit theorem. This is where we stopped last week. Perhaps you have seen, and I'm sure you will encounter, another formula for the confidence interval for the mean, which is the one given in this theorem. What's important is to realize what are the assumptions in statistics. So here, for the two previous cases, we've seen various assumptions. Here we assume IID data, so the data are independent and from the same distribution. This we have for all cases we saw on computing confidence interval. Plus, we assume that the distribution is Gaussian or normal. Those are two synonyms, at least for me, depending on the context. Some people make a difference between normal and Gaussian. For me, it means the same. So it's the Gaussian distribution. So if we assume we know this, then we can compute an exact confidence interval, which is not surprising. If we know the distribution of the data, then we know more, and we don't need to rely on asymptotics like we did a minute ago. The exact theorem is very similar with small differences. The estimate of the mean is still the sample mean. The estimate of the variance is almost the same with 1 over n minus 1 instead of 1 over n. I'll mention why in a few seconds. And then we have the results that this quantity here, mu n hat minus mu over sigma n hat times square root of n, has a distribution which is independent of the unknown parameters mu and sigma. I should have mentioned that before. If we assume the data comes from a normal distribution, the only thing we don't know are the mean and perhaps the standard deviation if we care about it. Here we're trying to estimate the mean. The magic thing is that this has a distribution which is independent of the unknown parameters mu and sigma. This distribution is called a student T distribution with n minus 1 degrees of freedom. So it's a standard distribution. What I call a standard distribution is a distribution that does not have parameters. For example, the standard normal distribution is the Gaussian distribution with mean 0 and standard deviation 1. So for every distribution, there is, if you want, one prototype, which is the one you have by giving default values to the parameters. So this one, student, is a standard distribution. That means we can look up a table. The only parameter we need to give is n minus 1, the number of data points. And since this distribution is known, we know with 95% probability in which interval it will be. So if we call eta a number such that this distribution is between plus or minus eta with probability 95%, we obtain this formula. So that is very similar to what we had before. We'll see where the difference is in a second. We have another result, which is that if we are interested in estimating the standard deviation with a confidence interval, which sometimes we want to do, most of the time we don't care. Most of the time we want to estimate the mean, and we use the estimate of the standard deviation as a way to quantify the uncertainty about the mean. In some cases, if you would also need to quantify the uncertainty about the standard deviation, you have this other result that says that this ratio, the standard deviation squared, so the estimate of the variance divided by the true value times n minus 1, also has a standard distribution, which is here chi-square with n minus 1 degree of freedom. So this is also a distribution that does not have any parameter other than n, the number of data sample. So same thing with probability 95%, we can give an interval for that, which gives a confidence interval for the standard, for the unknown standard deviation. Let's compare the two. We have seen two formulas for a confidence interval for the mean, one on the left we saw last week that I recalled a few minutes ago, and the new one that we have here. If I apply the formula with n equal 100, then we find here this interval, there is a square root of n that is missing here. I'm sorry, the square root of n is factored in this here. So we take 196 divided by square root of n, which gives this number here. If we compare the second theorem we saw about the similar case, we find this number, which is 198 divided by 10, gives this here. So this comes from the student distribution. This came from the Gaussian distribution here. The left here is not exact, is approximately true. The right is exact if we know that the distribution of the unknown distribution is Gaussian, which is a strong assumption. A second difference is about the estimate of the standard deviation. Here we have 1 over 100. Here we have 1 over 99. Where does that come from? Well, both have two different properties. If we take this estimate, 1 over 99, with a bit of work, we can see that it is an unbiased estimator of the standard, the square is missing here, sigma hat square. Voilà, sorry for the bug. Why the 99 here? It is because of this unbiased property. What does unbiased means? Well, remember that the data points are random. So when I estimate sigma hat, I have a random quantity. Hopefully it's not very random. If n is large, we hope that the variability of that is less than the variability of the data, but still it is random. Then it is a random variable, and we can ask, what is its expectation? What is its mean, its random mean? Then the expectation of this is precisely sigma square, the untrue but unknown variance. If we put 100, we will have a small bias here. So the expectation will not be sigma square, but 100 over 99 sigma square. So this is not unbiased. So some statisticians say it's a good idea to take something unbiased. Some others says it's not so important. Here it comes from another reasoning, which is called the maximum likelihood. We will come back to that when we talk about model fitting in a few more hours. So this comes from another reasoning by saying, if I want to estimate the variance, the most likely value that I can find is this one. So both have slightly different properties. Fortunately, when n is reasonably large, the difference between the two is negligible. So in reality, for what we do when we do performance evaluation, we don't care. We take one of the other formula. The main thing to remember is the formula on the left and the formula on the right give quasi the same, but the formula on the left is true only when n is large and the variance is finite and hopefully not too large. Formula on the right is true if the distribution is Gaussian. So there is this paradox that if you don't have one of those two assumptions, either n large or a Gaussian distribution, in fact, you don't know how to give a confidence interval for the mean. So we can see here the different random variable distributions that I mentioned, the Gaussian distribution. Of course, you use MATLAB or Python to find such values, but we know, for example, that with probability 196, the tail of the distribution leaves only 0.025 of the mass of the probability of being larger than 196 is 2.5%. Because the distribution is symmetric, it means the probability of being plus or minus 196 is 100% minus 2 times 2.5%, which gives 95%. This is why we often have this value. The second theorem we saw used the student distribution instead of Gaussian. So if we compare the values of the student distribution, we see that they are different, but when n gets large, they quickly converge to this value here. Voilà. So we have seen how to compute a confidence interval for the mean. Now let's apply this to something we very, very often have, which is estimating a failure probability. So we run a test for 10,000 instances. We want to try whether a system will crash, for example. So we test the system n times for failures, and we find 200 failures. Can we say something about the failure probability? Of course, the failure probability that we will estimate is 200 divided by 10,000, so 0.02, 2%. But we would like to say something about the accuracy of this 2%. We assume it's fairly large because we have 10,000, but we want to quantify. How can we model this? How does it fit in the framework that I've mentioned before? Well, this failure probability is in fact a mean. It is the mean of a random variable, of a binary random variable that has value 0 or 1. 0 if it's a failure, 1 if it's a success. Sorry, we should do the other way around. We should do 1 for failure and 0 for success, because we're interested in the failure probability. So for such a random variable, if p is the probability that the random variable is equal to 1, the expectation of xi is p exactly. So it's a mean in the sense of probability distribution. So estimating a failure or a success probability is the same as estimating the mean. How can we estimate the mean? Well, if we believe that n is large, which is the case here, probably, and if we believe also that the variance is finite, which is certainly the case because the values of are between 0 and 1, so there's no way the variance could be infinite. So probably we can apply the asymptotic theory, the theorem of last week. So the sample mean, number of failures divided by n, gives the estimate here. Then we compute the estimate of the standard deviation with this formula here. And we find some value here. We take the square root of this, we find 0.14, and we apply the formula with probability 95%. We multiply by eta, which is 196 here, multiply by this, divided by square root of n, that gives me this. 2% is the estimate of p, and the uncertainty is plus or minus 0.3% here. So, well, that is how we can apply this theory to quantify exactly a failure probability. So let's see if that works in all cases. I test the system here 10 times for failures and find 0 failure. Can you give a 95 confidence interval for the failure probability? I close the poll in a few seconds. And the majority says 0, 0, which sort of makes sense, because if we apply the formula, we have an estimate for the mean, which is 0, an estimate for the standard deviation, which is 0. However, if you think about it, a confidence interval 0, 0 means you're absolutely certain it's 0. Now, if you think about it, I mean, you did only 10 tests, you found 0 failure. Does it mean that there will be never any failure? If you think about COVID vaccine, we try it on 10 people, we found there is no side effect on 10 people. Therefore, the probability that there is never any side effect is certainly 0, right? That seems weird. So there is a catch here. There is a problem with this formula. So what is the problem? Well, the problem is that, well, we find not an undetermined, but we find a formula that doesn't make sense here. Well, what happens in reality is that here n is too small. Remember, this result is asymptotic only. It says if n is large, then we can apply the central limit theorem, like I did in the previous case. But probably here it's not the case because our formula is suspicious. Well, if we reason about it, what is happening is that if we do the same experiment not 10 times, but 30,000 times, for example, even if the probability of failure is small, then certainly we will find some errors. So we will not have an interval that will be 0. So the result will be different here. And we will see in a few more minutes how to know exactly what to do. But this should come like a warning for applying blindly formulas for confidence interval for the mean. Formulas for the confidence interval for the mean are always a bit tricky. You need to validate or have reasonable confidence that what you're doing applies here. Here it certainly does not apply. We could try the other theorem that we saw after that, which is exact, but applies only if the outcome of experiment can be modeled by a Gaussian random variable, which is not the case here. Here it's a 0, 1. It's a binary random variable. So we need another result. This other result is given here. When we have binary experiments, so we know more about the distribution. We want to estimate the probability of failure or the probability of success. It's the same. Then we have the hope of getting a theorem because we know the distribution. And therefore, we know also the distribution of the sample mean. If we count how many successes we had out of n experiments, we know that we have a binomial distribution. So this distribution is well known, so there is some hope. And this hope, which is not so easy to see, but the proof of this theorem is a bit tricky, and we won't go through it, but it works. It says essentially the following. A confidence interval is obtained by computing a lower and an upper bound that are given by this function of z, where z is the number of successes. We want to estimate the probability of success, and we've seen z out of n. So our estimate is z over n, but the confidence interval is obtained by applying this formula. L of z is given by this magic formula, the function phi, where the function phi is given by this other formula here, where little f is obtained from a Fisher distribution, yet another distribution. It's also a standard distribution. That's a distribution that has only parameters that are integers, n1, n2. So there's no need to specify a mean or variance, for example. So MATLAB knows about it. You also have tables about it. So you can apply this formula, and this will give the lower and upper bound here. In particular, if we have seen 0 success, which was the case before, we had done 10 experiments, we never saw a success or a test that fails, and we want to estimate the probability that a test fails, then we have, in this case, where z is 0, a confidence interval is 0 for the lower bound, like you gave in the quiz, but the upper bound is not 0, is this formula, P0 of n, which is exactly this, 1 minus gamma over 2 power 1 over n, where gamma is the confidence level we want. For example, typically 95%. And if n is large, it is approximately 1 over n times this, which is a constant here. So that is the exact formula we have. Now, whether n is large or not is easy to test, because now this is simply an arithmetic formula here. Second, this theorem says that when is the Gaussian approximation valid, whereas the previous theorem that is easier to use, when is it valid? Where it's valid essentially when the number of successes and the number of failures are not too small. So if we have practically at least 6 failures and not more than 6 successes, or vice versa, then the normal approximation is reasonably good, within a few percent of accuracy, which is the formula that everybody would tend to use. But that works only when those numbers are not too small. So if we come back to the example we had before, when we observe no event in n experiments, then a confidence interval for the probability of occurrence of the event is 0 for the lower bound, and this for the upper bound. And if we take as confidence level 95%, this is approximately this, 3689, which is yet another magic number, divided by n. So it decreases in 1 over n, not in 1 over square root of n, like for the other formula. So let's come back to my question before. We tested our system 10 times for failure, and we find 0 failure. Give a 95 confidence interval for the failure probability. I close the poll in a few seconds. %100% on the correct answer, which of course we obtain by simply applying the formula here. Requires a calculator. MATLAB or Python, we obtain this, which is, as you can see, is not so small. I do it 10 times, I never see a problem. That means with 95% confidence, I can say that the probability that I will never see a problem is 30%, which is still very large. So this is exactly illustrating what a confidence interval is about. It quantifies the uncertainty you have about your estimation. If we come back to the previous example we looked at, we had 200 failures, and we wanted to find a confidence interval for the failure probability. We used one method, which was based on the standard formula for confidence intervals for the mean. Now we know from this theorem, because z is larger than 6, and n minus z is also larger than 6, so we have 200 failures and close to 10,000 non-failures, so we are within the application of this. So we can apply this formula, and this formula is exactly the formula that we had before. In fact, it is exactly the central limit theorem and the approximation by a Gaussian random variable. So take-home message for this: if you have to compute confidence interval for a failure or success probability, then you can perhaps use the formula for the mean, but in extreme cases you will not, but there is another one that will be exact. Okay, take-home message at this point: confidence interval for median is easy to get, requires only IIDness, no other assumption. Confidence interval for the mean requires also IIDness, plus other assumptions like we have seen. And confidence interval for a success probability or a failure probability requires special attention when things are rare, when you're trying to estimate rare events. We have used the independence assumption. So we need to talk a bit about it. It's one of the assumptions we'll be making. We'll talk it in several phases. We'll talk about it a bit today. We've already started last week discussing what independence in a probability sense means. And a bit later, we'll see how to test whether data we have can be assumed to be IID here. There are several ways to know it. As I said, we can test, and we will see what kind of tests can be done. But tests are only tests. It's always good to reason about the data and see whether there is some hope that the data would come from an independent, an IID model, from a sequence of independently drawn random variables here. How do I know if this is true? Well, if I do a simulation, we'll talk about it tomorrow and next week, we must be careful to make it's easy to do if we know what we're doing. If we simulate things, then we can do what we call independent replications. Make sure that different experiments that we do are really producing things that are independent. Sometimes we can control the experiment. For example, if we can draw the factors randomly with replacement, or sometimes we can do the best as we can. And in that case, we can only infer. For example, we've mentioned last week that in order to avoid Simpson's paradox, it's better if the things that we assume can be drawn completely independently. For example, a hidden factor has no reason to take a value more than another. By shuffling the experiments that we do to distribute the random factors with equal probability, for example, or with a probability that's independent of the value of the factor that we care about. Now, one way to reason about it is also to realize what happens if the data is not IID. So non-IID data is the rule. I would say we need some work to make data that is IID. So that's the bad news about the statistical method. Much of the statistics assume that data comes from an IID distribution, or that there is independence somewhere. And most of the uses of statistics do not care about this assumption, except, of course, when people are very, very picky about the statistics, like in the medical sciences. When people do experiments, they will try to randomize all the hidden factors, and this is part of the validation test, for example, for vaccines. In engineering, most of the time people are less caring about that, and that may lead to wrong estimates. For example, it occurs very often that data is positively correlated. Positive correlation is one way to say that neighboring values look similar. For example, if you measure on a network the utilization of a link by counting how many packets are sent every millisecond, for example, and if you do that at high resolution, which we can do today because we are in the age of big data, so we can measure lots of things, we can store huge amounts of things, so we do. And then we will have high resolution data. Then for high resolution data, it is very frequent that the things are not IID. For example, if you measure the utilization of a link on a communication link, then there is buffering in the communication link. So there are physical phenomena that may correlate things over short time scales. If a buffer is full, then the output of a link is at the maximum link rate, and this will last until the buffer is no longer full. So if you measure things very frequently, you will see a very high utilization, one after the other. So this happens in a lot of high resolution measurements. What happens if we have positive correlation when the confidence intervals is underestimated? If I apply the formulas that we have seen with 100 data samples to compute the uncertainty I have, but in fact, intuitively, if the 100 data samples are positively correlated, that means that each of them is repeating a bit of the information of the previous one. So I don't have 100 new pieces of information, I have much less, because the second measurement I have is repeating largely the first one. So the amount of information that I have is much less, and doing 10 positively correlated measurements gives less information than doing 10. In fact, doing 100 positively correlated measurement, depending on the autocorrelation structure, may give us perhaps the same information as 10 independent measurements. So the confidence intervals are typically underestimated, which means we have much less certainty about what we're doing than what is in reality. Second thing to observe in order to reason about what independence means, independence is, in the statistical sense we have seen from the last week, independence means that is related to information. So here I'm proposing small variants of the interpretation we saw last week, and I'm asking you what you think about them. So the first interpretation I'm saying is that when my sequence is made of independent random variables, observing the n-1 first gives no information about the last one. Or observing the n-1 first gives no information when we know the distribution of xn, or that the conditional distribution of the last data point, given all the past, is a function of only the last data point. So what of those three statements do you think are true? I close the poll in a few seconds. And we see a large variance in the answers. Let's go through the different elements of answer. Oops. The first one, the second one is the easy one. That is obviously true. And that is the classical interpretation of independence. Independence has to do with information. A random variable xn is independent of a series x1 to xn minus 1 if there is no information, which means that if somebody reveals to us the values of xn, xn minus 1, and we have to do a prediction about xn, then that doesn't help us. That is what independence means. But there is a caveat. The definition of independence are always C. C is correct also, by the way. That's the definition of independence. We've seen there are multiple ways of giving the definition. With conditional distribution is perhaps the most intuitive one. It says the conditional distribution of xn, given all the other ones, in fact, does not depend on the values of the thing we condition upon. Having observed x1 to xn minus 1 gives us no information on what the probability is that xn will take any specific value, which is the true which is the classical interpretation of independence. Now observe that in order to make such an assumption, we need to be able to compute probabilities, which means that such a thing is true when we know the distribution of xn. Of course, if so, the correct answer to this is B and C are true, which means the correct answer is F, which is only 20% of the vote. About A, it's interesting to observe that if I know nothing about the random variables and I assume they are independent and coming from the same distribution, and if I don't know the distribution, by observing n-1 data points, I will gain some information about the distribution. In fact, that's what we've been doing when we talk of confidence intervals. When we talk about confidence intervals, we estimate the mean of the distribution, for example. So we will be able to give some information about the distribution, which also will help us get some information about xn. So in general, if a data sequence is IID, observing the more data points gives more information about the next one through the distribution. In data science, usually we assume that estimating the distribution is separate from estimating or doing a prediction, for example. So we estimate the distribution by observing a huge number of data points. And then we're at point B. Once we have observed a huge number of data points, then the only thing we can say about xn is coming from the distribution and not the specific values of those, but just how they are distributed. So this is the true interpretation of independence, which we need to remember because we will constantly be confronted with this concept in the rest of the course. Very often, people confuse confidence interval with prediction interval. In fact, if you read papers where they quantify the uncertainty, the difference is not very clear. If you read papers done by statisticians, of course, it will be very clear. But if it's done by engineers, sometimes there's a bit of confusion. So the best way to avoid the confusion is to learn about the two concepts. Prediction is something we'll talk about. That's an important topic in data science. We will see in this course the classical methods for predictions and the classical concepts more than the techniques. Here's one of the concepts. Assume I have a sequence of random variables, x1, xn, and assume that I have observed the first n1, and I want to say something about the n plus 1. Then one way to predict something, if the random variables are scalar, just numerical values, is to give a coverage interval, like we did for the confidence interval. So I say that a coverage interval, uv, which is built upon the data, so I make the dependence explicit here. I say that this is a prediction interval at level 95%, for example, if the probability that a new sample lies between those two is at least 95%. That's the definition about of a prediction interval. Like for confidence intervals, there are simple results and also complicated results. Here is the simplest result and the one that I recommend to use if you need to do a prediction interval. If the only thing you know is that the data is IID, coming from a sequence of independent outcomes that come from the same distribution. And assume you want to say something about a new data point. Of course, here, I assume I don't know the distribution. If I know the distribution, then I will say that this data point lies between the 2.5% and 97.5% points of the coverage points of the distribution. And that's all I will need to do. But of course, here I don't know the distribution. So based on the observation we did a minute ago, I can still say something. And this something is very similar to what we saw when we were trying to compute confidence intervals for the median, for example. It relies on order statistics here. It says that a prediction interval is obtained by looking at the order statistics. So I rank my data points, x1 to xn, and I look at the point with rank j and k, where the values j and k must be such that k minus j over n plus 1 is at least 95%, for example. For example, here, a very easy formula to remember. If I have 1000 minus 1 data points, the prediction interval at level 95% is the 25th and 1975th point here. Intuitively, it's very easy to understand why. The details are a bit tricky. There's always plus or minus 1 here. That's why I take 1000 minus 1. But intuitively, what am I doing when I do this? I have seen, roughly speaking, 1000 data points. What can I say about the distribution? Well, I can estimate the 2.5% quantile and the 97.5% quantile of the distribution by those two quantities here. This is an approximation of the two quantiles, like we do in a box plot here. And then, approximately speaking, if this approximation is good, if this estimation of the quantile is good, a new data point with probability 95% will be between these 2 points. Well, here the theorem says that it's true, except you don't take 1000, but 1000 minus 1. This is exactly what this theorem is saying. So this is a first thing. In practice, this requires n to be large. For example, if we want to have a prediction interval at level 95%, and if we have 39 points, the only thing we can say is between the mean and the max. which is a bit disappointing, but that's the only thing we can do. For n equal 10, for example, we cannot even have a prediction interval at level 95%. So this is the very simple formula. I don't go through the proof of it. The proof of it is very similar to the kind of things we did to prove the confidence interval for the median. In fact, the formulas are based also on order statistics. For some reason, this is very often what is not used. In engineering, most of the time we use standard deviation and mean for historical reasons, probably. So here is an exact result for a prediction interval that applies with high restrictions, normal. So normal here means Gaussian. So here we made the problem easy by assuming I want to guess a value, predict a value of a random variable, having observed n, and I know through some out-of-band mechanism that the distribution is Gaussian. The only thing I don't know is the mean and the standard deviation. Well, we could say, well, estimate the mean, estimate the standard deviation or the variance, and then that will give us the distribution, and then the answer is finished. This theorem is a bit smarter. This theorem captures the fact that the mean that we estimate is not the true mean. So mu n hat are the standard mean, the sample mean, so the average of the n first value. Sigma n hat square is 1 over n minus 1, etc., the estimate of the variance, the unbiased estimate of the variance here. Then the theorem says that with probability 95%, for example, this will be between those two bounds. The value, the unknown value will be between those two bounds here. And for large n, this is approximately the sample mean plus or minus eta, which is 196, times sigma n hat here. So in some sense, if n is large, this is saying that the prediction interval at level 95% is mu plus or minus 196, the estimate of the standard deviation here, or sigma. This is not surprising, right? This is what we do if we assume that out of the nth point, we have a true value mu and s. The unknown values are estimated and we ignore the error. Then this is what we can say. If somebody says to you, here is a random variable that has a Gaussian distribution with mean mu and standard deviation s, then with 95% probability, it lies between those two bounds. So the second part here is essentially what we get if we ignore the uncertainty. The interesting thing here is that this captures exactly the uncertainty of estimating the parameters here. Here's an example. Here we have measured file transfer times for a number of points, and we're interested in finding a prediction interval here. So here I did it with 3 methods. I'll show the third method in a second. The first method is giving the value here and the prediction interval for the value here, using the first theorem, the order statistic. Out of the n data points, I look at the 2.5% lower, the 97.5% upper, and that gives me this coverage interval. This is the method I obtain if I apply the previous formula, this formula here, the standard mean plus or minus 196, the standard deviation here. Here, you will see that the two methods do not coincide at all. Right? This interval is way larger. In fact, this interval does not make sense. The second interval, it gives with very large probability negative values, not very visible, but 0 is here. And if you look at the data here, I'm sure you should, it's not easy to see, but you see there is a red point here at the top, which means this is typical of a distribution which we can call heavy-tailed. We'll come back to that topic. It means most of the values are somewhere here in the lower range, around between 0 and 200, let's say. And very few points are extremely large, but in a very small number here. This is also a symptom that the variance of this distribution might be very large. And probably also that distribution is not Gaussian. Why do I say very probably this distribution is not Gaussian? Well, because for a Gaussian distribution, the probability of being larger than 6 sigma, for example, is extremely minuscule. It is 1 minus 99.99%. So for a Gaussian distribution, seeing things that are very far away from the cloud of where the points are is something extremely unlikely. If you have 1 zillion points, you will see a few of them, but if you have 200 points, it's very unlikely that you see one of them. So if you do see one of them, the most likely thing is that your data is not Gaussian here, which is compatible with the fact that this prediction interval does not correspond to this one here. This prediction interval is exact. Probability 95% will be here. This one is approximate, is exact if it would be Gaussian, otherwise it's only approximate. I realize I just invalidated this quiz. So let's, of course, here, A is not a valid prediction interval because of everything I've said before. So one technique that is very often used by statisticians is to make the data look more Gaussian by changing the scale. So very often when we do measurements, we measure things and then we keep things in how we usually do. But sometimes it's useful to think about what is the scale in which I measure. For example, if I observe the performance of a web server, I can measure the average time for processing a transaction, or I can measure the average number of transactions per second, which are related by 1 over x time rescaling. Similarly, if I measure some noise somewhere, I can measure the power of the noise or the log of the power of the noise in decibel rather than watts, for example. So there is always the scale that needs to be asked. Now, very often the physical property of the system we have impose a scale. Everybody uses the same scale, so you have to do it. But sometimes if we want to do statistical processing of the data, it is worth perhaps thinking about rescaling. Rescaling is, for example, instead of looking at the data, look at the log of the data or the inverse of the data. In general, we can have this type of transformation, which is called the Cox transformation, which is a continuous set of transformations with parameter s, which is a power of s, and in the limit when s goes to 0, it gives the log. Let's see here what happens if I take, for example, the log of the file transfer time. On the left and on the right, I have exactly the same data, except if you want, on the right, I'm showing them in log scale here, which we often do, right? When we have data that have a large range, large variability in range, we tend to take a log scale. If we take a log scale, then this is what we will obtain here. I plot the log of the data, and we see that the log of the data doesn't have outliers here. So what I could do here is compute the mean and the standard deviation of the log of the data and apply the formula for a prediction interval. And then take the exponential of this interval. That will give me this, which is a much more reasonable performance here. How would you do that? I hand wave and say, let's take the exponential of the log here. If you want to compute this thing here, how would you do it? Here I'm proposing 3 methods. Which one do you think is the right thing to do? I close the poll in a few seconds. and the majority says C, which is, of course, the correct answer. Log of the data, I would not say appears to be normally distributed, at least does not violate like the original data, the assumption that it's normally distributed. Therefore, if I call Y the log of the data point I have on the right here, I can apply the method we've seen before, estimate the mean, the standard deviation, and then with 95% probability, the Y values will be between those two things. Now, if I want to come back to the data, I can do monotonic reverse transformation, which is the exponential. Since this is monotonic, going from Y to X preserves the probability. But of course, we need to take the exponential of the bounds here. So this is how we can obtain this better prediction interval. Voila, we'll do a little break. And after the break, we will come back to the topic of how we can test such things, whether the data is normally distributed for such predictions. So we have seen that taking the log of the data may lead to radical computation of a prediction interval if the data, and this was based on the fact that the data could not reasonably be assumed to be normal. How can we check whether some data is normally distributed? There are two methods. One, which is old style, but still works very well, is visual inspection by using a tool called the QQ plot. So what is a QQ plot? That's a term that we will very often find. The QQ plot is a tool to check one distribution against another one. And the normal QQ plot is a plot that tests a distribution against Gaussian distribution. It's done by taking on the x-axis, so I have a set of data points, x. On the y-axis, I will plot the order statistics, so the sorted set of data points that we have very often used so far. And on the x-axis, I will take this. Those are the standard estimates of the quantiles of a distribution. So if I have n data points, capital F is the CDF. I invert the CDF. I obtain points here that are not exactly the quantiles, but they are estimates of those sorted points here. So if the data here comes from this distribution, capital F, then the little x and the large X should be very close to each other, which means that the points, the cloud of points that I obtain by plotting on the x-axis little x, on the y-axis, capital X, I should have something close to the diagonal here. If it comes from exactly capital F, it will be the diagonal. If it comes from something that deviates from capital F by a shift, a rescaling, and an offset, which is the case from, in other words, in the case of a normal distribution, if it comes from a distribution that differs from F by a mean and a standard deviation, we will find a straight line, which might not be the diagonal here. So let's do that, for example, for the data point that I have here, the set of data points, I did this QQ plot. So this is the blue line here. So this is QQ plot given by a standard tool, in this instance here, MATLAB. MATLAB automatically does a straight line fit. So it tries to fit this cloud of blue points to a straight line. And we can discuss whether the set of blue points seems to be well aligned. And here we see, obviously, no, there is a very visible shape at this point here. This plot here is very different, which means that the quantiles of our distribution are much larger than the quantiles of the what we would have if it would be Gaussian, which corresponds to what I qualitatively said before. Finding a point that is so far away from the rest of the other point is extremely unlikely. So this is visible here by the fact that the red line, that is the best that MATLAB could do in fitting here, is very far away from the blue point, from the blue points here. If I apply this to the log of the data, which this is what I obtain here. Right? So we can see, well, it's not good because it doesn't align, but remember that things are random, right? If I here, the little xi are a theoretical value, which are the best estimates that we can do, maximum likelihood estimates of the sample quantiles that we obtain here. So we don't expect a perfect fit. In fact, if there is a perfect fit, it means that your data was not random. So it doesn't come from a Gaussian distribution, because a Gaussian distribution produces some randomness. Here is, for example, one QQ plot I obtained by plotting points that I have generated with a random number generator. We'll talk about it in the next lecture. That is supposed to follow a Gaussian distribution here. So we see what we expect in terms of randomness. Qualitatively, we should expect that you don't see a big deviation from the straight line, but you should see some. Of course, what I'm saying is a bit frustrating. I'm essentially saying we're in the world of big data and data science, and we still do things visually. But even statisticians today consider our neural network might be better at doing that than other artificial intelligence systems. So it still makes sense to visualize the data, and it will be extremely easy to plot here non-Gaussianity here versus that. Of course, this idea is encapsulated in tools that will try to automate this thing. Instead of simply looking at it, we can do a number of quantitative criterions that we measure about this plot to see whether it looks more like this or not. So we'll talk about this when we talk about tests a bit later. But right now, it's very useful to know that there is this tool to compare a set of samples against one distribution. I would like also to come back to a little observation. I said very often people are not very clear when they write papers how they measure the uncertainty. Here are two measures we will find very often. I measure some data, I find a sample mean mu. I measure the standard deviation, I find some estimate S. Then I can plot the uncertainty by this formula. This is very often done. Sometimes people use this formula. Now, what are those two formulas? Well, we know that the first one is a confidence interval for the mean. It is true if the data is finite variance and n is large, or if the data is Gaussian. And the other one is a prediction interval at level 95% as well. And it assumes the data to be Gaussian here. The difference between the two is the square root of n here. So this is quantifying the variability of the data, assuming it's Gaussian, which most of the time is an assumption you will need to verify, because many things are Gaussians, but many things are not Gaussian as well. And this is something that's reasonably true when n is large. We've seen exceptions when we're trying to estimate rare events, but otherwise this is most generally true. But of course, there is a square root of n, and this is capturing the uncertainty about mu, not the variability of the distribution here. So that's the distinction between a confidence interval and a prediction interval. And we've seen also that computing a prediction interval with this formula is very risky. It assumes the data to be Gaussian, but we have seen that there is another formula based on order statistics. So you might say, well, at the point where we are now, we have seen a bit confusing formulas. There's the mean, the median, the prediction interval, the confidence interval. What should we do about that? Aren't there too many? Well, in fact, there's much more many than what we've seen. Of trying to zoom on the really essential ones, which to me are the most useful ones and the most used ones. The most useful ones are the ones that are robust. The most used ones are the ones that use L2 norm and statistics based on estimates of variances. We will see that the robustness is not always in favor of the latter ones. So what we will discuss now is this issue of robustness. Here, I'm assuming here, for example, an example where I'm drawing a number of samples from a distribution, which we will talk a bit more in a few more hours of lecture, which is a Pareto distribution. It's not Gaussian, it's Pareto. And this Pareto distribution has the property that it can produce that the extremely large values are rare, but not extremely rare, unlike what happens for a Gaussian distribution. So most of the values are small, but a few are large. Here I'm showing confidence interval for the mean and for the median. When I do 100 samples, so this is an artificial data set that generated data with the computer from a fixed distribution. And of course, I know the mean and the parameters of the distribution, but I try to estimate them here. Now, the true median is this value in blue, light blue here. The true mean is here. If I try to estimate the confidence interval for the mean here, I have a coverage interval that does not contain the true value here. So I have an embarrassing problem. If I try to estimate the confidence interval for the median, we see that the true median is in the coverage interval. And if I do something that we will discuss a bit later, bootstrap estimates, those are estimates that tell us whether the value for this confidence interval here is correct. And this is correct if the central limit theorem occurs, which means that my estimate of the standard mean should be Gaussian, should be normally distributed. My original distribution is not Gaussian, but we know that if we apply the asymptotic value for confidence interval for the mean, we are using the central limit theorem that has the conclusion that the n is large. When n is large, the distribution of mu n minus mu rescaled by the estimated standard deviation is approximately Gaussian. So if this is true, I redo the same experiment a large number of times. I plot the value obtained. I do a QQ plot, and if it is true, this QQ plot should follow should show a Gaussian distribution. Here we see that there is there is clearly a shape, a systematic deviation. This was for 100 samples. I do it again for a large number, 10,000 samples. And here we will see that it's even more clear that the central limit theorem does not apply here. We see that in that case, the coverage interval is perhaps not correct, but the true mean is still inside it, but the true median does not have the problem. So first take-home message here. Well, when distribution have a very large variance, which is related to seeing rare events, then those things based on the mean are extremely non-reliable. They might not give good result. Whereas the ones that are based on the median and the order statistics they don't have this problem here. Why is it important? Well, it shows up when we have what we call outliers in distribution. Outlier here is one value. So I'm just showing again the data that we have seen before. That's exactly the same data, the log of the data for the file transfer times, the QQ plot shown, and the QQ plot of the log of the data. The QQ plot shows data is not normal. Now, in fact, this data was sanitized. There was one value that was extremely large, and as we do when we have large data sets, we try to eliminate values that seem incorrect. Now, this is, of course, sometimes very safe, sometimes very risky. I mean, is the value incorrect, or is it a correct measurement? When we measure, for example, file transfer times over the internet, if we see a file transfer that lasts for 12 hours, is it an instrumentation error, or was there really a big file transfer that lasted for 12 hours? If we look at the data in detail, usually we will find out what has happened. But when we have big data, we typically don't look at the data in detail. We have to apply algorithmic methods. So let's assume here that I did not remove the outlier, that I compare the data with or without the outlier. So if I remove the outlier here, I will have a QQ plot that is equally non-Gaussian, but I will have data that look a bit different. Of course, my plotting software computes the y-axis scale automatically to fit all the data. So we see here that the scale is slightly different here. Of course, in log scale, what was an outlier might not look like an outlier. So it doesn't care so much here. So let me look at what I obtain if I compute different things. Confidence interval for the median with the outlier present or with the outlier removed. We see that they are the same, undistinguishable. If I compute the confidence interval for the mean with or without the outlier, we see that there's a huge difference. There's a huge difference on the mean and a huge difference on the standard deviation that translates into a huge difference into the coverage interval, into the confidence interval. So that's the first take-home message. Well, The methods that are based on mean and standard deviation are extremely sensitive to outliers. But of course, whether a deviating value is an outlier or not, we don't really know. The ones for the median are not here. So this is when we try to estimate the central value of this distribution. If we try to obtain a prediction interval, we find exactly the same thing. The prediction interval based on the order statistic is not influenced. In fact, what happens if we think about the mechanics of order statistic, we rank the data and we eliminate the two ends of the distribution. So the outliers are automatically eliminated here. So they don't play, they play a very minor role. They might change a bit the rank of some of the data, but they will not change, they will not have a significant impact. As for here, the prediction interval that uses the formula for the standard deviation is extremely impacted. The mean, as we said, is impacted, but the standard deviation even more, because the standard deviation uses an estimate of the square. So if one value is large, the square of this value is extremely large. And interestingly here, if I rescale the data by taking the log, of course, the impact of the outlier is much less because I've compressed the data with the log here. Well, what is the take-home message here? Well, methods based on quantiles and order statistics are robust to outliers. They should be preferred whenever you have a choice, right? There's no reason, if your software or your environment allows it, there's no reason to use other methods than those here. Methods based on mean and standard deviation are sensitive to our outliers and make assumptions about distributions. Therefore, they should be used with care. So we'll conclude with this last philosophical quiz. Since methods based on mean and standard deviations are less robust, why are they used at all? I close the poll in a few seconds. And here is the distribution of the answers. Here, there's no really correct answer. It's a matter of opinion. So in opinions, we don't know what is right or not. But probably all of this is true. There is a large amount of intellectual laziness or simply imitations of what has been working so far. Still, it is true also that there might be cases where it's much more efficient to use mean and standard deviation because they are more compact, for example, and they can be computed online, right? If you update a mean, then whenever you receive new data points, you can do an update to the mean you had before, and that will give you an online algorithm. Whereas, of course, if you need to increment the order statistics, you need to keep at least an approximation of the entire histogram. This is doable, and some papers propose how to do it, but this is certainly more if you want to do elementary things, it's easier to do here. So the restrictions that your computing environment might impose to you might be good reasons for studying mean and standard deviation. We'll see also there are cases where theories exist for the mean and standard deviation based methods and not for others. That might be another reason. So the philosophy of this course, I'm not trying to preach, use this or use that, but I'm just trying to, based on experience I've seen in large number of projects done here and there, try to see what statistics teach us and what in the current state of affairs, state of science today, what is best for us to use and what is things to be careful about. In particular, one of the methods I would like to, or the meta statements I would like, is use methods that you understand. When I say, what do I mean with that? Well, you don't need to be able to prove the central limit theorem to use the standard deviation, the confidence interval for the mean, for example. That's not what I mean. But what you understand, what you should understand is what are the assumptions that are made when using this method. For example, when I compute a prediction interval mu plus or minus 196 sigma, I am assuming the data is Gaussian. Do you know what this means to be Gaussian, or do you have ways to detect whether this is true or not? If you don't, then it's risky, right? You're like a medical doctor who uses a medicine because another doctor uses it, but doesn't know what the side effects are or what are the things that it's good for. So you should understand when the method is applicable, and by understanding the assumptions that are made here. Voila, that's all for today. So that's the end of the lecture part of today. The rest of the time for today is devoted to doing exercises. Since we're all online, you'll have to do them online. Those exercises are not just, some of the questions are just answering a poll, but some will require really some computation that you need to do on paper at home. So they require more time than the quiz that was done last week, for example. But they really will have you put the fingers on the methods that are used for summarizing data in this lecture we saw today. Voila. So enjoy the rest of the exercise, and see you soon. Bye-bye now. Of course, I and the TAs are now online until the end of the slot, so until 4 o'clock. So we're here to answer your questions.